Hi, my name is Onyekachi Ibe, and my presentation is on the regulation of the gastric phase of digestion. Before diving into the gastric phase itself, it's important to understand the broader context. Digestion is divided into three phases: cephalic, gastric, and intestinal. The gastric phase starts when food physically arrives in the stomach and stretches its walls, triggering both mechanical and chemical responses. At this stage, the body must precisely regulate the release of acid and enzymes to effectively break down proteins while also protecting the stomach lining from damage. This tight regulation is handled by three major systems: neural inputs, especially through the vagus nerve, hormonal signals like gastrin and somatostatin, and local reflexes that respond to the stomach distension and changes in pH. If regulation fails, it can lead to clinical issues like gastric ulcers or indigestion. That's why the regulation of this phase is so critical, because it's not just about digesting food, but doing it safely and efficiently. What happens during the gastric phase? The gastric phase kicks in when food reaches the stomach. At this point, both mechanical and chemical digestion intensify. Mechanically, the stomach begins to contract, churning the food with digestive secretions to form a semi-liquid substance called chyme. Chemically, several cell types in the gastric glands go to work. Parietal cells release hydrochloric acid, which creates the low pH environment needed to denature proteins. Chief cells secrete pepsinogen, which is activated into pepsin by HCl and begins protein digestion. Meanwhile, the presence of partially digested proteins stimulates G cells to release gastrin, a hormone that further boosts acid secretion. Altogether, this phase typically lasts several hours and it sets the stage for efficient nutrient digestion in the small intestine. In the gastric phase, regulation depends on a coordinated network of specialized cells. Parietal cells are responsible for secreting hydrochloric acid, which not only creates the low pH necessary for digestion, but also activates enzymes and kills pathogens. Chief cells secrete pepsinogen, which becomes pepsin in the presence of acid and begins protein digestion. Gastrin, a key hormone released by G cells, ramps up both acid secretion and stomach motility. Histamine from enterochromaffin cells or ECL cells works synergistically by further stimulating parietal cells. Meanwhile, mucous cells protect the stomach lining from damage by forming a thick alkaline mucus barrier. Finally, these cells release somatostatin, which acts as a braking mechanism, suppressing gastrin, acid, and histamine release when the stomach becomes too acidic. This delicate balance of stimulation and inhibition ensures digestion happens efficiently but safely. Neuroregulation of the gastric phase operates through both central and local pathways. The vagus nerve, part of the parasympathetic nervous system, plays a dominant role by releasing acetylcholine, which stimulates parietal cells to produce acid and encourages overall gastric activity. At the same time, the enteric nervous system, often called the brain of the gut, carries out local reflexes within the stomach walls. These reflexes are triggered by the distension of the stomach and the presence of peptides. We can think of the neural input as being divided into short reflexes happening entirely within the gut and long reflexes that involve the brain, especially during the cephalic phase, which can spill into the gastric phase. Together, these neural signals help fine-tune the stomach's secretory and motor responses to food, ensuring everything stays tightly coordinated. The hormonal regulation of the gastric phase is a finely tuned feedback system. Gastrin is the star hormone here, released by G cells in response to peptides and neural signals like vagal stimulation. It promotes acid secretion, pepsinogen release, and gastric motility. Histamine produced by ECL cells works hand in hand by binding to H2 receptors on parietal cells, significantly amplifying acid output. But to avoid overacidification, these cells release somatostatin, which acts as a regulatory off switch by inhibiting gastrin, histamine, and acid secretion when pH gets too low. These hormones don't work in isolation. When gastrin, histamine, and acetylcholine are all active, they create a synergistic effect that results in maximal acid production. This balanced hormonal interplay ensures the stomach digests efficiently without harming itself. To function properly, the stomach relies on tightly integrated systems of neural, hormonal, and local mechanisms. These systems coordinate based on what kind of food is present and how much. For example, protein-rich meals stimulate more gastrin, which increases the acid and enzyme release to match the digestive load. But too much acid can be harmful, so the body relies on feedback loops, like somatostatin secretion to keep things in check. When this regulation breaks down, we start seeing clinical conditions like gastritis, GERD, or peptic ulcers, especially in the presence of factors like H. pylori infection or chronic NSAID use. Understanding this regulatory network is critical in clinical practice, forming the foundation for treatments like proton pump inhibitors, H2 blockers, and somatostatin analogs that help restore balance. As we've seen, the gastric phase of digestion is a beautifully complex system where neural, hormonal, and local factors converge to optimize digestion. Gastrin, HCl, and pepsin are key agents, but the role of inhibitors like somatostatin is just as vital. They protect the stomach from its own secretions. Disrupting this balance can lead to serious conditions like ulcers and reflux. To help connect the dots, I've included a case study for you to walk through on your own. It's a chance to apply what we've covered to a real-life scenario involving gastric hypersecretion and their diagnosis. Thank you so much for listening, and let me know if you have any questions. And these are my citations. Have a good day.